In today's session, what we'll be discussing, we'll be learning about how do we build our own social distancing tracker, right? And the agenda for today's session is we'll start by talking what is social distancing. We'll discuss what is object detection. We'll understand what it is, how they work, what are its practical implementations, right? And then these concepts will better help us understand how does social distancing detection algorithm works. Okay, and with this concepts, we'll further move into an hands-on session to implement this algorithm ourselves, which we will be doing using our live camera. Okay, now talking about what is social distancing. So social distancing is a method which we use to control the spread of contagious diseases, right? As people maintain physically distance among themselves. So we understand that this COVID-19 pandemic has made government and officials to implement these social distancing rules into the public places, right? By maintaining it, they ask us to maintain a distance of 6 feet amongst themselves so that we can we can avoid the community spread, and this will in turn help us to open the places safely. Right now, when you think of an AI which will do the social distancing tracker, right? So an AI, a camera which is tracking social distancing, the first thing which will come to your mind is that the AI should have the capability to detect humans, right? It should be able to see where the humans are walking. It should be able to recognize and identify them. And to do so, what we have, we use object detection model, right? So we use object detection model on the given frame, which helps us to identify humans in the frame. Now, in computer vision, you must have heard and listened of lots of object classification tasks, right? So there are various kinds of object classification tasks. It's like what we call hello world problem in the computer vision. But do you understand what is the difference between object classification and object detection? So to help you understand it more better, you can see we have demonstrated it through a picture here. So on the left hand side, you can see a cat. So what this object classification model will do, it will identify the object in the image, right? So it identifies that, okay, this image has a cat to it. Whereas object detection models helps you to identify as well as localize that object within the image, right? So you can see it will identify that, okay, this image has cat, dog, and duck. Whereas it will also go further and tell you at which position, at which location they are present, right? So this position is represented through an anchor box. So these bounding boxes, what you are seeing here is an anchor box. And if we implement same object detection technique model to a video frame, right, it becomes an object tracker. So here I have put a basic video of object detection model, which works live from the video camera feed. So you can see here in the real time, it recognizes all the objects within the environment and it draws the anchor bounding box within that. Right. So this is how the object detection model works in real time. Right. So you can see it is able to recognize and detect. Now, if you talk about what are the steps involved in building this object detection, right? So if you need to have this object detection model, how they works, how it is being implemented, right? So what we do, we first take an input as an image, then we apply region-based CNN to generate multiple regions from this image, which are nothing but the subsegments, right? And then we use a technique by which we combine all these similar regions based on their color, texture, shape, and size, compatibility, and similarity. Okay, so you can see on the left-hand side image here, right? Sorry. Yeah, this black and white input image. So what we do, we take it as an input image. We apply region-based CNN net. We apply this, we feed this image to a region-based CNN network. And what it does, it extracts and gives us the sub-segments within the image it identifies it and recognizes. Those segments we then just combine based on their similarity of shape and size to create a larger region. This region is nothing but our object location, what we call it as region of interest, right? So this region of interest is actually those anchor bonding boxes it identifies through it. And then we send these region of interest to the CNN model to further classify which class they belong to, right? And what we do overall is that once we have all these regions classified into these classes, we combine all these regions to form our original image and the detected objects, right? So I have also explained similar thing in the diagram here. So we take a raw image, we apply this convolution network to the image. This convolution network is nothing but a region-based CNN network, which helps us to propose and extract the region of interest. So these region of interest are the object location for us, the anchor boxes, right? The boxes which has the objects to it. And then we send these region of interest through to a ROI pooling layer. So what is this ROI pooling layer? So ROI pooling layer is nothing but again a region of interest pooling layer. So if you imagine, given this image, it will extract the anchors, right? And different anchors will be of different pixels and shape, right? So ideally, what we do, we convert all these different images to a single shape, right? A fixed shape through padding and through apply pooling, max pooling technique to it, and we fixed its length. Okay, and that fixed length is fed through a convolution layer, because that's the prerequisite. Convolution layer only accepts the features represented with a fixed dimension, right? It will not accept features with a dynamic dimension. So we fix the features for our ROI layer, and then we feed it to a fully connected layer. On top of fully connected layer, we have two classifiers to it. One classifier will help. One is an softmax classifier, which helps you to detect and identify what that image is, whereas another is a linear based classifier. So it will predict the bounding boxes of the anchor, right? So given the image, this object detection model will help you to identify where the objects are. Plus, it will apply softmax to it to identify what that object is, right? And to talk more about that, there are various state-of-art models available to help you do object detection tasks. So here you can see a comparison has been drawn based on the accuracy of models like faster RCNN, SSD model, YOLO model. SSD stands for single shot multi-box detector, and YOLO stands for you only look once. Right, so these are the various state-of-art models. State-of-art, when you listen of the term state-of-art, so what it means in the sense is that state-of-art helps you to understand the performance of model is equivalent to human performance, right? So the way the human works and understand their mind interpret is the same way the model works. So here you can see the accuracy we have drawn with respect to different pixel size, right? Different images size with 300, 512, and with and without. So you can see a star marks there. That is with and without an augmentation. Right, so the values you can see here is within all the similar range, like 70 to 80, and these values represent mean precision of the model, right? So that's the evaluation metric we consider for these object detection models. And based on what we choose and so basically these all models are trained on different data sets, right? They all have different classes available to it. So based on what your use case is and what's your computation power is, you decide which algorithm and which model to use. Okay, and all these models are available open source and are pre-trained through deep learning various frameworks, like you must have known of PyTorch, Caffe, TensorFlow, right? So all these models are available within this framework. So you can, and that to a pre-trained. So we use this pre-trained model for our task to build our application on top of it. All right, and in specifically for our object, for our social distancing tracker, what we will be using SSD model. SSD is a single shot detection model, which was invented in December 2015. And there has been research going on, and researchers have made lots of progress in this. Last year and this year, last month, there was YOLO version 5 being released. Right, so there is a constant research happening to this field. And to talk more about that and to understand what it is this single shot detection model and why they work, let's talk more detail into this. So basically, if you talk about single shot multi-box detection, what they mean in the sense, single shot signifies that the task of object localization and classification is done in a single forward pass, right? So you have a single model. You can see in the diagram below I have put, it's just a single model. Through one forward pass, it does both the localization through identifying the region of interest as well as doing classification on top of it. Okay, and multi-box in the sense because it is very class agnostic in terms of predicting the bounding boxes, right? So given the image, it also draws a bounding box where it has to predict the X and Y values. right? And detector, as the name itself says, this is a classification. So all those regions are then classified into the objects we have trained for or looking for. And to give an overall high level picture, you can see we take an input image, say 300 cross 300 size. We feed through a mobile net network. This mobile net network extracts the region of interest from the image. Then we pass this region of interest through an SSD model, through which we finally get the detections classified, right? So you can see here overall what this model will give you. This model will give you total 8732 anchor boxes detected for a single class, right? So these many anchor boxes, and if you think how these many classes, so you can see here the classifiers takes a convolution of 3 cross 3 filter, and the filter size is a parameter of 4 cross under bracket classes plus 4, right? So what is this? So now 4 represents simultaneously below here 6 represents, right? So what these numbers represent number of anchor boxes for that particular region. Classes represents the overall categories you have for the model, and this 4 represents the offset you have from the bounding boxes, right? The X and Y values. So if you calculate overall with the classes this model was trained on, so basically this model was trained on Cocoa dataset, which was open sourced by Microsoft. It has over 80 classes to it. And if you calculate and get the final value, it will help you to end up with 8732 anchor boxes per classifier. And then what we do, we apply a non-max compression technique on top of it. So what is this non-max compression technique? This non-max compression will help you to ignore the bounding boxes which are significantly overlapping, right? So you can just imagine there is 4 bounding boxes which are overlapping and they have significant area captured to it. So we just ignore and capture them as a single. So likewise, we just end up with a single bounding box, right? So with this, if you think of how do we build a social distancing algorithm, the steps will be look very straightforward, right? So we start with taking an input image video, let it be a recorded or a live stream. Then what we do, given the frame, we first detect objects to it, right? So given the frame, there will be multiple objects to it. We'll only filter it to detect the humans, the persons. Based on the detected persons, what we will do, we will compute pairwise Euclidean distance between the centroid of their anchor boxes find. So you can just imagine yourself within the screen. You can just imagine there is a frame of a video, and then there is say 2 persons identified with the background, or cars to it, or trees around to it, and then the object detection model identifies these 2 persons. They draw the bounding box around it. Then you consider the centroid of this bounding box. Take the Euclidean distance between the pairs of it, and then the value what you will be getting from the centroid of their distances will be in pixel. So we will rescale this pixel value into centimeters to then further draw a conclusion whether they are maintaining a social distancing or not, right? So to summarize this, we take our input image or video frame, we apply object detection, filter it only for persons, we apply Euclidean distance on top of them, then we convert those distance value to centimeter and then draw a conclusion, right? And to give a very detailed high level picture of how the algorithm works. So basically first we start by calibrating the camera, right? And to calibrate the camera, let us assume that the person is standing as a distance d from the camera. Okay, let us assume that this distance d is 400 centimeters. Okay, next let us consider the person's actual height in real is h. Okay, and based on general statistics, we assume that let the average height of humans be 165 centimeter, right? Now the object of the person we identify, right? So using object detection model, we can also identify the pixel height, the height of the person in pixel through the bounding box coordinates we will be achieving, right? And using these 3 values, we can we can calculate the focal length, right? So focal length is the formula of focal length you can calculate is using the pixel height of the person into the distance from person is standing divided by the actual height of the person. Okay, so this value will help us to get you the pixel, the focal length, and this focal length will help you to then calibrate the camera well into the real world. Okay, so this calibration, why it is important? Because you need to convert your pixel values into real numbers, right? Into real world numbers. So it is very important. You need to first calibrate your camera before building any computer vision task, especially to our social distancing detection. After adjusting our focal length, as you can imagine, a person may move far or away to the camera, right? So to further calculate their distance, we use something called as triangular similarity technique. So this triangular similarity technique is a similar way how do we calibrate our camera, and to determine the distance of the person from the camera, we use the actual height of the person, what we assume 165, the pixel height of the person, what we get from our object detection model, the coordinates of the anchor points, and the focal length of the camera. So basically focal length, as we understand, will be achieved through our so-called step one, right? What we discussed. So using these three parameters, we can calculate the distance, the real depth of the person in real time, at what distance they are achieving. That too using a monocular camera, right? And then these values will help us finally to get our X, Y, Z, right? So what is this X, Y, Z? So X, Y coordinates are our anchor box, right? As we discussed, we considered the centroid of the anchor boxes. So through which we get our X and Y values. Initially, these values, X and Y values, will be in pixels. We convert it through triangular similarity into centimeters. Then through again we have calculated the distance of the person through camera, which gives us the depth. So we have also our Z coordinate. So using this X, Y, Z coordinate, we apply Euclidean distance between all the persons detected in the frame, right? Considering their centroid, we calculate Euclidean distance for all the frames, and we convert these pixel values into centimeter. You can see the equation I have mentioned here. So you feed your pixel value, you multiply it to the distance to the camera it is achieved, and divided by your focal length. So the resultant value will be the conversion of your pixel value into centimeters, right? So it depends. If your distance, the default metric, the default metadata of your distance is centimeters, it will be written in centimeters. If the default metric of your distance is you have kept in meters or say feet, it depends on what values you are considering and assuming assumption starts with, right? So we convert these values using this similarity technique, and once we identify the distance, we straightforward use a simple logic. If the distance between person is less than say 2 meters, 200 centimeters, or 6 feet, we draw a red bonding box in front of them. And if it is not, we draw a green bonding box, right? And if a red bonding box is drawn, the person, the social distancing is violated, right? So to summarize and keep it very simple, you can understand. We apply object detection, we detect the humans. Within the anchor boxes detected, we calculate the Euclidean distance. We convert the Euclidean distance into centimeter for the real world conversion. And then we compare if the distance is maintained or not. And if it is not maintained, we say it is violated by drawing a red bonding box. If it is maintained, we say it's a green box, right? So with this, let's jump into our code. So code I have open sourced here. So I request, let me put this into chat. So you can directly go and clone this repo. And let me also do the steps in front of you. All right. So first, let's look into the repo. Okay, simultaneously, you can look into the repo here. So what all do we have? So here you can see we have SSD mobile net model, right? So what is this SSD mobile net model? So this is the object detection model we talked about, right? Single shot multi-box detection. This is the SSD pre-trained model we have, which was pre-trained using CAFE, right? So CAFE is one of the framework. Along with this pre-trained model, we also have a model configuration file. So if you look into this configuration file, it contains the dimensionality, right? So if you remember this diagram, what we were referring to in the SSD model, this is the same configuration we have defined. So it has the dimensions to it, it has the weights to it, whether padding was there, whether striding was there, what is the pooling layer applied. So these are the very basic how convolution works. These are the parameters what we define to it. And with this, we have our class labels. So this SSD pre-trained was pre-trained with 20 classes, and you can see the name of the classes here, right? So there is actually 19 classes and one background, right? So it classifies background separately, and then aeroplane, bird, cat, bottle, and the thing we are looking for is person. So if you consider, if you think in terms of programming, thinking of it starts with index 0, your person is at index 15, right? You can see your person. So the index 15 of class is your person. That's what we are concerned about, right? And then looking into, there is also requirements.txt. So we use computer vision for our for working with the video frames and doing the detection and prediction part. And we use NumPy for the basic number crunching and calculating our Euclidean distance. Okay, then we have one test video, test sample, right? So in case you have a camera within your system, I suggest use the camera and run the program. If you don't have the camera in your system, you may use this recorded video to see how this in real time works, right? Before we get into this, let's first look into the program. How do we code it? The social distancing, right? So this is under social distancing detection.py. So as we know, in Python, we start by importing the libraries. So we import our computer vision library, we import our math for basic computation, we import our NumPy library. Then we start by defining our argument parser. These argument parsers are generally useful when you run your programs through command lines. So the arguments we give is like a video, right? Whether you want to give a recorded video or a live video. Your model file, right? Your pre-trained model file, your pre-trained model configuration files, right? We looked into the labels, the label file, right? And the confidence score. At what confidence do you want to classify, or do you want to consider the prediction, right? So these are the basic parameters. Sorry, these are basic parameters we consider. Then we start by loading our model. Right, and to load our model, we use a readnet from Cafe. It's a function available as part of computer vision CB2, and the arguments it takes is like two arguments. It will take the configuration file of the model, and as well as it will take the model file itself. We load our pre-trained model to a variable named so-called network. Okay, then after loading our model, we feed our input source. Okay, so as on the defined on the argument video. If you define a video, it means you are giving a recorded video. If you ignore the video parameter, it will by default consider that you are using your camera. Okay, so we assume that you are using your camera, and we take the input. We'll start capturing the input continuously. We'll be recording it. Okay, and we'll convert and we'll store it into the frames. So this input, what we are reading, will return two values. The first value is whether you are having a value. It's a binary, true or false. The second frame is nothing but an array. It will capture the values in an array and store it in frame. Then we identify the height and width of the frame, right? Our pixels height and width. Then what we do, since we are using SSD MobileNet model, these models were pre-trained on features on image sized to be 300 cross 300, right? And what we do, so we resize our image. So to resize our frame to 3 cross 300, we use a function called blob from image. So this blob from image is a function available again as part of computer vision. So it takes 4 parameters to it, right? So what are these 4 parameters? Your first parameter is your frame itself, right? The frame what we have captured, the input. The second parameter is the rescaling. At what factor do you want to rescale your values, right? Your NumPy arrays values. So we rescale it to a factor of half of 255 by 2, right? So generally we understand that in RGB we have 0 to 255 pixel values, right? So we consider half of 255 and then consider half of that to rescale it to the values. So we get a very small numbers and then rescale it to a similar range. Then we consider the size itself. So the input size of our image, we have resized it to 300 cross 300. And then we take the mean of the RGB values. So these are the 4 parameters we feed to the blob from image function. And this resize image what we achieve, we store it in blob variable. Then what we do, the model what we retrain, this model has a function set input to it, right? So we set the resized image as an input to our network. Then we apply a forward function to it, right? So as you remember, we discussed in SSD, it's both localization and classification happens in a single forward pass, right? So we apply a forward function to it, which is as part of the network we have created, right? So the network what we have defined initially. using our CV2 ReadNet model. This class has these functions of set input and forward. So what this forward will do, this forward is nothing but a predict function, right? So you do prediction on top of the blob input you set, and it will return three values to it, right? So the network.forward will return three values. So what are those values? Your first value will be your X and Y coordinates, your bounding box, anchor box coordinate. Your second value will be your confidence. So you remember we used a softmax classifier for classifying the objects, right? And softmax classifier will give you a probability score. We use that score as a confidence for that prediction. So that's the second value, and third value is the class itself. What was the class predicted? Right? So we store all these values to a variable named detection. So detection has all the prediction results available to it. Then what we do, we create a dictionary called postdict, and in this dictionary we store our XYZ value in centimeters. Right, so we will calculate our X and Y values from our anchor boxes. We will get Z value from the distance, which will be in pixels. We'll again convert those values through triangular similarity into centimeters, and then we'll store it into postdict. And these are the values we will be using to compute the Euclidean distance, right? So you understand the formula of Euclidean distance. It comes like under root x1 minus x2 whole square plus x2. So the formula goes like this, right? I have not unable to write it here, otherwise it would have been better. So we all know the formula of Euclidean distance. So we use this x, y, z coordinates for the same. And then what we do, we have calculated. So we pre-assumed that the distance of the person from camera is 400 centimeter, and real height of the person is say so-called 165 centimeter, right? And if in such configuration, if you look into the object detection, if you just run a trial, you will perceive that the pixel height of the camera will be somewhere around 240, 250, right? Considering these values, we calculate the camera focal length to be 615, right? Then once we have identified and calibrated our camera and got the prediction value, we loop over our predictions, right? So we loop over. So here you see we have considered the shape of 2. Shape of 2 in a sense for the number of objects detected in that frame, right? So we start iterating over those detections. We first extract what is the probability associated to that prediction value. Then by default we assume that let's say the probability is above the 0.2, right? You can adjust this value. We have considered a parameter here, right? Argument of confidence through which you can adjust to say 0.9 or 0.5. So here say the value, the confidence is above the threshold. What we do, we extract its class ID. Okay. After extracting its class ID, we'll compute its X and Y value. These X and Y value will be our anchor box coordinates, right? You can see start X, start Y, end X, end Y, right? So this will be our anchor box coordinate predicted. Then based on all the objects detected, as we see here, trained for 20 classes, we'll only filter it for person. Right, so the person class was 15 here, so we will filter it for the person 15 ID, and then we'll draw a bounding boxes based on the coordinates we have got. Right, so there is a function called rectangle which takes the argument of the frame and your coordinate itself with the color of the box you want to draw. Right, so it will draw the bounding box and it will give you that okay, this is a person. Then what you will do, you will store these values into a variable into a dictionary coordinates. Why? Because then we'll further do the basic computation on top of it, right? So as we discussed, we compute the Euclidean distance from the midpoint of the coordinate, the centroid of the anchor boxes, right? So we calculate it using the basic averaging formula by start x, end x divided by 2, and we round off this number to a decimal place till 4. Okay, so we compute the midpoint of the bounding boxes. We also require the height of the bounding box, right? So we calculate it by cruising through subtraction of end y and start y, and again rounding off till 4 decimal places. Next, what we'll do, we'll also calculate the distance of the person, the depth of the person from the camera, and we use it using the formula we have seen before into our algorithm. So 165 comes from the distance of the height of the person. F is the focal length of the camera, and height is the height of the pixel, height of the person in the pixel. Using this, we find the real-time distance at what persons are standing in. And then these x and y midpoints, what we calculated, the coordinates, the centroids, we again convert them using the same formula into centimeters. So this will give us our x, y, and z. Then what we do, we compute. Here you can see finally we are computing the Euclidean distance. So we compute the Euclidean distance between this x, y, and z values. And then if the distance between them is less than 200, we store those coordinates into our close objects. It's a variable we have defined. And then what we do, if we have a coordinate identified in close objects, we draw a red bonding box to it. Okay, so here you can see RGB, right? So we draw a red bonding box. If it is not, we draw a green or blue bonding box to it, right? And then finally, what we do for better visualization, we convert our centimeter values to feet, right? For better visualization and analysis of the distance. And further, what we do, if you want to close the system, we have defined a basic function to quit it, right? So this is how the overall we have defined the algorithm. Now coming back to our implementation. So I hope everyone have installed Anaconda to their system, right? And set up done the prerequisites. Have you guys set up Anaconda? Okay, nevertheless, let me continue so we can look at later. Okay, so let's start by implementing this, right? So as I have shared the prerequisite, you guys should be having Anaconda installed, and if you have Anaconda installed, you will have the Python available to you, and you can see a base. This represents the environment, so you have a Python Anaconda environment to it. Now let's run it, right? So to run it, what we will do? We will first clone our repo, and how to clone it? Let me just show you. Yeah, so you can just copy this. You can type here git clone. So we'll clone the repo, all the pre-trained models, all our files. Okay. So if you have done the same, I suggest you also follow the same on your side, so you can simultaneously do and test it on yourself. Okay. Once we have cloned the repo, we'll change the directory, right? So we'll go the directory we have named is social distancing. Once we have gone into the directory, let me first show you. Okay, so my camera is busy here, so I'm not sure if it will again detect. Let us test. It will be an interesting test. Okay, my mistake. Okay, right. So I've given the command here. You can not to worry much. You can just copy the command, and you are there in the folder. Let's paste this. Let's try. Okay, yeah. You see, there's an error showing, right? So why it shows an error? Because I'm using my camera here, right, through the live streaming. So the port is busy. So it's unable to take here. Unfortunately, not the live feed. Let me show you through recorded camera, right? The video that we have recorded. So if you run this, it will, yeah, you can see it's detecting the depth in real time, and it's also giving you the distances, the probability of person detected and what the distance they are maintaining. And if the distance is less than 200 centimeter, a red bonding box is detected, right? So, and then to close the system, you can just Control C as we have defined it. So for now, I just showed you using your MP4 recorded video, but I suggest you implement, you run this. I have posted this repo in the chat. You can copy this, and within this, you have the presentation and all the pre-trained model and the code itself. Right. So ideally, what will happen is that finally you can let me go to. Right, so this is the model and code available here. You can copy paste. Right, so finally talking about the deployment, how do we use it? Right, so as we said, the very first and important need is to calibrate the camera. Right, so we need to calibrate the camera to very well map the pixel distance into the real world distance. Right, this is the first step. Second step, as we have seen here, the cafe models are very lightweight. Right, so as I have discussed at the beginning, we used here the SSD mobile net model. So why SSD mobile net model? For two reasons. First, of course, it has the persons as an object available to it, which is the recognition, which is the objective of a task. Second model, it is a very lightweight model. Okay, on very less. When I say lightweight, it has very less parameters to it. Second, given on a low resource computation power, like embedded devices, like assuming Raspberry Pis and Jetson Nanos, Jetson TX2, right? So those low embedding devices, it can run very well, and you can see you can achieve a FPS, frame rate per second, of say 40 to 60. That's a very good to achieve in lightweight processor, and that's where SSD models are very are the favorites when you talk about you doing object detections on embedded devices. And then, as we have seen previously, that if the distance was less than 200, we draw a red bonding boxes to it. Instead of the red bonding boxes, you can have any triggering action attached to it. Say an alarm being sent. Say you have deployed this application into your Raspberry Pi. Say you have an office on all the CCTV. You made the detection, and then what you do, you have the camera doing the tracking, and then if they detect if persons are not closer, they send an alert to the authorities that at this place these many people violated, and you can also then display the image, what was the image, what was the face of the person, and then they can further very well track to which all persons in contact they have come, if they have any coronavirus, right? So such way you can do re-identification of persons and very well track how the community spread and how the persons being tracked, right? So with this, we have come to an end. So yeah, that's what I mostly wanted to show. Right? So any questions? Was it good? We still have 5 more minutes to go. Right. Right. So you can just let me know if you have any questions or want to discuss on something. I have posted the repo on the GitHub repo on the chats. So you can very well clone it and try it yourself, I would suggest. And you can embed and try it on the Raspberry Pis or small devices itself and see how they work in real time, right? So any questions do we have? Yes, the PPT is available in the GitHub repo itself. You can download from there, right? I have posted it in chat. I hope you guys are able to see the chat.
One of the attendees asked which camera.
It can be any camera, any 2D camera, right? So you can assume a web camera, a USB based camera. You can also Raspberry Pi has a CSI camera. It's any camera it will work on, right? You just need a 2D camera.
One of the attendees asked about the commercial deployment. Any commercial deployment?
Yes. So as we discussed there, right? So commercial deployment is very well can be done, and that's the purpose. So ultimately, the two things you need to take care. First is that you need to very well calibrate the camera in real time, and second thing, by adjusting its focal length. Second thing, you can use any low embedded devices, and you can have a triggering action on top of it. And very interestingly, yesterday I have seen there is a robot wandering around in Chennai contaminated zone. They had this social distancing AI algorithm to it, so it roams around real time in the contaminated zone. Police don't have to interfere and get themselves in danger. So robots goes into the contaminated zone, convey the message, and see if the persons are doing social distancing or not, right? So depending on the use case, how you want, whether you want to fit it on a robot, a drone, or a surveillance, general surveillance CCTV, it can be anywhere.
One of the attendees asked, what is the accuracy in real-time scenario?
Yes. So the accuracy is as we say, these are the SOTA models. So when you say SOTA models, the first thing is that it will identify above 95% with probability, the confidence, the humans. Once you have identified the humans, if you have very well calibrated the camera, you can achieve 100%, above 95% accuracy.
And one of the attendees asked, what is the approximate processing CPU power required for this?
Yes, so as we understand that anything what we in real time, it should be achieving anything like 40 to 60 frames per second, and low resources power, anything like 1 GB of RAM with your Broadcom processor should be good. But I would suggest try with Jetson Nano to be to the least. And if you are using Raspberry Pi, say 1 GB 1 GB RAM, then you can have a neural stick or a Coral. Google has a Coral board. So basically, these are neural sticks which comes with the processing of more numbers. So that will increase your FPS if you are finding it low in your devices.
Rohit have asked, can I implement it with Pi 0?
Rohit, Pi 0, of course, you can implement, but Pi 0 has lots of drawbacks. I would suggest not to do. right? But you can definitely.
Drone, can this algorithm work?
Yes, with drone, definitely this algorithm will work. You need to have a bit of change in the calibration, right? So as you assume here, we assume that the person is within straight within us, right? But in drone, the angle will be a different, view will be a different. So you just need to rescale the view and recalibrate it. Rest the algorithm remains the same.